Hello, Professor. My name is Prundarika Kadam, and today, along with my team members Sai Sharanya Vamshi and Sai Avinash, I will be presenting our research on spoofing detection methods for biometric systems. This research focuses on enhancing the security and the robustness of biometric systems against spoofing attacks, which are attempts to deceive the system using fake biometric samples. So, biometric systems are widely used for security purposes due to their ability to provide a high level of security based on unique human characteristics. Common biometric modalities include fingerprints, facial recognition, iris scanning, and voice recognition. Despite their advantages, these systems are vulnerable to spoofing attacks. Spoofing involves the use of fake biometric traits, such as artificial fingerprints or facial masks, to deceive the system and gain unauthorized access. Our primary objective is to develop methods to detect and prevent spoofing, ensuring the robustness and reliability of biometric systems. Traditional machine learning techniques offer promising solutions for enhancing spoofing detection. Current spoofing detection methods face several challenges, including low accuracy in distinguishing between genuine and spoofed biometric traits, poor robustness against sophisticated and adaptive spoofing techniques, and computational inefficiencies that affect real-time processing and detection. These challenges significantly impact the overall security and reliability of biometric systems. So, our goal is to enhance the accuracy and robustness of spoofing detection systems by developing methods that can adapt to evolving spoofing techniques and perform efficiently in real time scenarios. So let's review some key studies in the field of spoofing detection. The first study by Jane focuses on the use of local binary patterns or LBP to differentiate between genuine and spoofed fingerprints. LBP has proven effective in capturing the texture features of the fingerprints. The second study by Sanderson highlights the advantages of using Gabor wavelets for reconstructing fingerprint rich details. Gabor wavelets enhance uh, the intricate details of fingerprint images, aiding in better spoof detection. The third study by Kang explores dynamic thresholding methods to adaptively respond to varying spoofing techniques, enhancing the system's ability to detect new and sophisticated spoofing attacks. So, our objectives for this research are threefold. First, we aim to conduct a comprehensive review of current spoofing detection methods used in biometric systems, analyzing their strengths and weaknesses. Second, we perform a detailed analysis of the techniques used in the fingerprint recognition for spoofing detection, identifying key features and metrics that contribute to successful detection. Third, we plan to design and implement new algorithms aimed at improving spoofing detection, with a focus on enhancing accuracy, robustness, and computational efficiency.
Hi, I'm Sharanya. Let's talk about the overview of the model we built. To develop an effective fingerprint spoof detection system, a diverse dataset of genuine and spoofed fingerprints was collected. This dataset was then pre-processed through resizing, normalization, and augmentation to ensure consistency and enhance model performance. Feature extraction methods, including local binary patterns, ridge pattern detection, and minutiae extraction, were employed to capture critical fingerprint characteristics. Support vector machines and random forests were trained using these extracted features to build robust classification models. The performance of these models was evaluated using accuracy, precision, recall, F1 score, and ROC AUC metrics, ensuring that they effectively distinguished between genuine and spoofed fingerprints. Now I'll elaborate more on these topics. Coming to data collection and pre-processing. For data collection, we focused on building a large and diverse database of genuine and spoofed fingerprints. Genuine fingerprints were sourced from various biometric datasets to capture a wide range of demographics and conditions. For spoofed fingerprints, materials like gels, silicone, and other synthetic substances were used to replicate common spoofing techniques. This varied dataset ensures that the model can effectively identify different types of spoofing. Coming to pre-processing, to standardize the size of the fingerprint images to match the input requirements of the machine learning model, we use resizing. This step is crucial for ensuring consistency and allows for the uniform feature extraction across the dataset. Resizing can be done to a fixed resolution or using a method that maintains aspect ratio and important features. Normalization is used to adjust pixel intensity values to a common range to reduce variations caused by different conditions. This step can improve model performance by ensuring that the input data is uniform and reducing the impact of environmental factors on feature extraction process. Normalization also enhances the ease with which the model can distinguish between real and fake fingerprints as it scales the pixel values to a standard range. Augmentation is used to apply various transformations to fingerprint images such as rotations, flips, shifts, and zooms. Augmentation artificially increases the size of the dataset by creating variations of the existing images, which helps the model generalize better to new unseen data and improves its robustness against minor distortions and variations in the fingerprint images. Coming to feature extraction, we use local binary patterns for texture analysis of fingerprints. Unlike previous methods that measure gray tone variance, LBP compares a pixel's intensity with its neighbor, creating a binary pattern that captures the fingerprint's microstructure. This binary pattern is then transformed into a histogram that reveals the frequency of microstructures. LBP effectively highlights subtle textural details that are often altered in spoofed fingerprints, enhancing the system's ability to distinguish between real and fake fingerprints. Additionally, we employed ridge pattern detection to identify the main ridge patterns and minutiae points in fingerprint images. Ridge patterns, including ridges and furrows, provide unique details to each individual. The identification of the minutiae points, such as ridge endings and bifurcations, is crucial for comparing genuine fingerprints with fakes. Minutiae point extraction involves identifying key points like ridge endings and branch points, which are essential for fingerprint matching. By analyzing these points and their positions, we can compare them to patterns from genuine fingerprints. This process helps in detecting discrepancies that may indicate spoofing, ensuring that the model can recognize high-quality replicas and maintain robust authentication. When it comes to model training, we used machine learning algorithms capable of handling complex, high-dimensional data to distinguish between genuine and spoofed fingerprints. Support vector machines, or SVMs, were chosen for their effectiveness in managing nonlinear relationships between features. SVMs create hyperplanes in multi-dimensional space to separate different classes, and the kernel trick was employed to manage nonlinearity in decision boundaries, improving the model's ability to distinguish between real and fake fingerprints. Additionally, random forests were implemented due to their robustness and ability to capture intricate feature interactions. This ensemble learning technique builds multiple decision trees during training and classifies by voting on the most frequent outcome among all trees. Random forests are effective at preventing overfitting and provide reliable classification results by considering various feature interactions and maintaining generalization across different data scenarios. Coming to the training process, model training and testing were conducted using Python's scikit-learn library. Key stages included hyperparameter tuning, cross-validation, and performance evaluation to ensure robust spoof detection models. Hyperparameter tuning optimized models by adjusting parameters like the SVM's penalty parameter C and kernel type, and random forest number of trees and depth. Cross-validation, particularly k-fold, was used to assess model accuracy and prevent overfitting by partitioning the dataset into multiple subsets for training and evaluation. This approach ensured the models generalized well to new data and reduced the risk of overfitting. Thank you. The following parts will be explained by Vamshi.
Here we are going to discuss about the model evaluation. Access performance using accuracy, precision, recall, F1 score, ROC. Accuracy, measuring the overall correctness of the model by calculating the ratio of correctness classified instance to the total number of instance. but it may not be sufficient if the data set is imbalanced. Precision. Calculating the ratio of true positive to the total number of positive prediction made by the model. Recall. Uh, Measure the ratio of true positive to the total number of actual positives. High recall means the model identifies the most of the actual spoofing fingerprints. F1 score provides a single metric that combines precision and recall, offering a balanced measuring of model performance. The receiver operating characteristic curve plot and true positive rate against the false positive rate at various threshold settings. A high AUC indicated a performance indicating between the two classes across the different threshold. Then going to the next slide. Novel spoofing detection method. To enhance fingerprint spoofing detection, we development and advanced approaching integration the improved feature extraction method with the machine learning models. Transforming filters future distinguish fingerprints variation and detecting spoofing. We overall our framework characterized and advanced feature extraction, hybrid machine learning, and dynamic threshold demonstration supervise the flexibility and stability compared to extraneous methods. It effectively handles a various spoofing scenario, providing a more reliable and secure biometric identification system. Then going to the next performance results. The new method distinguishes integrate advanced feature extraction techniques and sophisticated machine learning modules, resulting in a significant high detection rate. In incorporated deserve a set of spoofing scenario into the training of machine learning methods, which is a uh, support vector machine and random forest. The comparative training ensured that the models are not only effective against knowing the spoofing methods but also capable of generating the new or unscenario spoofing techniques. Uh, Traditional methods often struggles, which is a highly variability and suitable spoofing attempts, which is techniques providing a foundation they lacked and capability required to effectively counter more sophisticated spoofing methods. Then going for the next slide, discussion. The finding from the study revealed that integrate and advanced feature extraction techniques with the model machine learning model significant enhance the accuracy and robustness of biometric spoofing detection. This advancement of highlighting the effectiveness of new methods in handling a wide range of spoofing techniques, thereby offering a better protection of a biometric system. First of all, strength. The proposed method offers several advantagements of over traditional approaches. The integration of advanced feature extraction techniques provides more details and accurate text representation of fingerprint patterns. The hybrid approach, which is a combination of different machine learning modules, improving the system reliance against various spoofing techniques, addressing previous limitations such as handling of desired spoofing scenario and reduce um, robustness. Overall, the new method providing a significant upgraded in both detection accuracy and system stability. Then after limitations, despite the strength, the proposed methods having limitations that need addressing. One challenge is need to be extensive resources and time to retain the maintain complex machine learning modules. Future mode, the real time capable of these methods in various conditions remaining the critical, ensuring fast, reliable, and performing deserve environment challenging. For future work, future researchers such should be several keys spoofing detection future. Additionally, ongoing research should be address the involving nature of spoofing techniques by continuously updating the methods to revert the protection and new sophisticated spoofing effects. The next slide will be explained by my teammate Avinash.
Hello everyone, myself Sayavinas. Now I am going to explain some of the important code snippets in our project. So the picture shown here is for extracting three main features in our project. So the first one is LBP features. LBP stands for local binary patterns. So from the code, we are going to create an empty list right here, and we are going to run an for loop, and then we are going to create an instance of local binary pattern, and the features are converted right here into the histograms and converted into float data type. And here we are going to normalize the features, and then we are going to append the features into the empty list and returning them as an numpy array. So the second one is the ridge pattern features. So for that we are going to use Gabo filters. So right here we are going to create an empty list, and we are going to create an instance of Gabo kernel, and then for loop is ran. And here we are going to use an 2D filter for the Gabo filter, and the extracted images, sorry, the features are flattened and appended into the empty list. And finally we are going to return the features as a numpy array. So the third feature is the deep features using VGG16. So the VGG16 is a pre-trained model on ImageNet. So here we are going to create an instance of VGG16, and here we are going to create an empty list, and then for loop is run for extracting the features. So in the for loop we are going to convert the grayscale image into the RGB image, and then we are going to change the dimensions of the image, and then we are going to extract the features and return them as a numpy array. So this is with the extraction of three main features in our project. So the next one is the training. So we have used four main algorithms. They were logistic regression, and the SVM support vector machine, the random forest, and the k nearest neighbors. So we have chosen these four algorithms. So the algorithm which has got the highest accuracy, so we are going to consider that algorithm. So here we are going to fit the model, and here we are going to predict the the classification, and then we are going to check the accuracy right here and creating the confusion matrix and also the classification report. All these were written at the end of the function. These are some of the important code snippets, and the next one is the implementation. So now I am going to show the demo of our project. So I'm going to choose an image called image1, and I'm going to upload the image. So it's showing as image uploaded successfully. Now if I try to upload any other image rather than the image1, it is going to show an authentication failed message. So you can see that authentication failed. So if I upload the same image, you are going to get the authentication passed message right here. So this is with the demo of our project. So this is with the demo, and coming to the conclusion. So the traditional machine learning algorithms that we have used in our project shows the enhanced highest improved security for the biometric systems, and future directions further research to address emerging spoofing techniques and optimize real-time performance. So that's it with the conclusion, and thank you.